All right, 99. Since you asked so nice, let's see. Bring it up. Oh, so the chance of an IRS audit for a tax return is about 2% per year. We are interested in the expected number of audits a person has in a 20-year period. Assume each year is independent. So I've got the probability of an audit in any given year is 2%. They gave me 20-year period, so N is 20. You guys with me? Maybe. The first couple are the same kind of questions you keep seeing everywhere. So I don't know if you had trouble with those. In words, define the random variable x. So I mean, what would x mean in this case? Do you guys know? First off, what's a better symbol for 0.02 in terms of a binomial situation? So,
Percent?
No, what's the variable for it? So if I'm looking for people that are going to be audited, is that a success or a failure? Success. That's a probably getting audited. So what symbol am I gonna give it? P. What would Q be? Probably a failure, which in this case would be 98. I like it. Just to remind you guys, success doesn't mean happy times, right? In general, I would not call being audited a success. But since the question is looking for audits, that is what we define as a success. Could be rabid squirrels, could be dead people, just whatever I'm looking for. Okay, what values? So X, what's the letter X mean in general for these kind of problems? Number of successes, because that's what can change. So what values could X take on? Sing it.
Anything from 1 to 20?
Almost, not quite. Everybody always leaves out the chance that you are not audited at all. So anything from 0 to 20. I like it. Let's be more optimistic. Okay, let's stop for a minute. So everybody with me on this. So this is what I call an NPQ problem, otherwise known as binomial probability. Where are we at? Blah, blah. I mean, you've seen this earlier. Remember, I don't know if you guys have really seen this yet. Whenever they say describe the distribution, it could be binomial, and then they want NP. It could be something we're going to talk about uniform today. We're going to talk about uniform, normal, right? It's a good old bun. All right. Okay, maybe. So that was the next question, is describe the distribution, which is really what we did here, to be honest. How many audits are expected in a 20-year period? The expected value. What's the expected value another name for? The more general name for expected value. Who remembers? We learned this in chapter 4. I love you guys. You guys doing all right? No, shit. All right, I'm sorry. I know I'm a big part of that reason you're not doing well. So happy I could be here for you. But what's another name for expected value? A statistical name.
Average,
The mean. The mean is the expected value. So again, if the average age of Grossmont is 27, and I took 80 Grossmont students, what average age would you expect them to have? 27. That's the expected value. The average is the expected value. So they're asking me to find the expected value for this, the average. What is the formula for the mean for an NPQ problem? Such a beautiful little formula. N times P, because why does it make sense? 2% of the time you'll be audited. So over 20 years, 2% of 20, N times P. Don't even need the formula's help for that, right? So you just do that, is that cool? So I don't know, I'm just going through the whole thing. I don't know which part you had trouble with. And then the standard deviation, is that what they asked for next, maybe? No, they don't. Find the probability that a person is not audited at all. What would X be in that case? This is part E. X would be 0. And the probability formula is this funky ass one we did last time. N choose X, P to the X, Q to the N minus X. You guys remember that? If you weren't here, if only I posted video. Oh yeah, I do post videos. Okay. So you just got to throw shit in there. So now I know what N is, I know what P is, I know what Q is, and I know for part E what X is. Just throw it in. Is that cool? Is that all right? And then the last one is find the probability that a person, now I love this question. So part F is find the probability that a person is audited more than twice. What does more than twice mean in this case exactly? More than twice. 3, 4, 5, up to 20. So you could do a formula for 3, do a formula for 4, do a formula for 5, all the way up to 20, add them up. You could. What's the opposite of more than 2? 0? 1? 2. I like it. Another way to say what's the opposite of this is what does this leave out? This leaves out 0, 1, and 2. So I could do 1 minus the probability of 0, 1, 2. So instead of doing formulas for 3 up to 20, I could do formulas for 0, 1, 2. And on part E, I already did 0. So I really just need to do that formula for 1, that formula for 2. Add them up. That's the opposite answer, 1 minus. So that is the general idea. Anytime I have a probability question, I'm like, holy shit, that's going to be a lot of work to answer that question. What's the opposite? Oh, there's a lot less work. Do that. Right? Do the opposite. And then do 1 minus. And then you've got the answer. I don't know if you guys get that. So the at least one thing is just the most generally used application of that. But that idea is broad. It's anything. But do you guys get that this question is asking more than 2? So you would have to do that formula for 3, that formula for 4, and add them all up. Is that cool? I'm just giving you another option. You can do that. You can totally do that. Show all your work. But I'd much rather do the opposite, which only has 2 things to do, because one of them I already did on part E. Does that make sense?
I was just kind of confused on part E and F.
That's what I'm talking about. Is it what I'm saying making sense?
A little bit more.
Okay, a little bit more. Well, part E is straight up.
Yeah.
You know X is 0. Bam. Throw X in there. Throw N, P, and Q in there. Do it. Kick ass. This is the funkiest one, should be. So I'm going to do the probability of 0, which I already got from whatever that is. Probability of 1, so now I'm going to make X 1. And the probability of 2, add all those up. That's the opposite of what the question wants. So then I just do 1 minus what I get, and I've answered the question. Because again, let me show you another visual. What's all the possibilities for this problem? 0, 1, 2, 3, 4, 5, up to freaking 20, right? Right? Where's at least, greater than 2 would be all these. So I could figure out all these probabilities and add them up. That would answer the question. Nothing really wrong with that except, holy shit, you're wasting your time. But, it's still work that'll get you to the answer, so. I'd much rather realize they all add up to 1. So 1 minus this has to equal this. Of course it does, right? If all of these add up to 1, then 1 minus any piece of it equals the other piece. That only makes complete sense. So either way you want to do it, it's fine. But I would probably do it that way. Right? Do the formula for 0, which you had to do for part E anyway. These are the only 2 extra things you got to do for part F. Add them up, subtract it from 1. Maybe. Okay. Anything else? Any follow-ups to that or something else from homework stuff? Yes? Oh yeah, did I ever tell you guys? I might as well tell you. Did I tell you about this I? I did. So if you're over that way, you might want to say something. I did tell you about this I, right? Okay. So I can't see that way very well, which is really exciting for walking and driving. So which one? 88? Okay. The one about the Vietnamese New Year. The one about the 12 students, which 88 in chapter 4?
Oh, yeah.
Okay. So this one's almost exactly like the one we just did. Thank you. So this is the one about they surveyed 12 students to see who will attend the New Year festivities. She knows that 18% of them will attend, right? So what do we know so far? What's 12 and what's 18%, 0.18? What variables? Say again? N, good. And P, I like it. So what's Q going to be? 82. Right? I'm not going to point out that you guys just used the 1 minus thing that I keep going back to, but I guess you did. What else did it say? Blah, 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 blah. In words, define what X is. So X is the number of successes, so it would be the number of people that might go. Right? What values can X take on? Anywhere from 0 to 12, blah, blah, blah. Right? Could have nobody go. You could have up to 12 go. You guys with? Okay. Blah, blah, blah. The distribution we talked about a minute ago. How many do you expect to attend? Again, that's the average, right? Mean is N times P. And then the last 2 questions are very similar. Find the probability that at most 4. How do you write at most 4 mathematically? At most 4.
Less than or equal to 4?
Yes, that's the most it could be is 4. So less than or equal to. So to do this, what do I need to do the formula for? For X equal to 0, 1, 2, 3, 4. Real quick, now watch. The opposite would require me to do 5, 6, 7, 8, 9, 10. Oh shit, no, let me just do the 0 through 4. So yes, you do have to do the formula 5 times. 0, 1, 2, 3, 4. If you need to cry about that, feel free. Just don't get on your paper. I only see those tears. All right? Only actively, not aftermath. You guys with me? And then what's really nice about this is part E, I think it is, part F says find the probability that more than 2. And again, we just did this one, right? More than 2. What's the opposite of more than 2? Don't say less than 2. That's wrong. What's the opposite of more than 2?
0.
And 2. So less than or equal to 2. And what kicks ass about this is you've already done the work for that. Right? So you might cry here, I got to do 5 things, you suck, Jeff. And then this one is like, oh, I already did the work for that shit. Hopefully you stop crying. Yes, maybe? Maybe? Yes? Maybe not. Okay. Anything else from homework stuff? But I really want you to see what I just did. Here, I considered the opposite, and it had more work. So screw it. I'm just going to do that directly. Do you see what I'm saying? So it's not always one or the other. It's think about it. Oh, that's kind of a lot of work. The opposite has even more work. Shit, I think I'm okay with this now. Let me just do this. Okay. All right. Are you guys, let me see. Remember, you can make corrections to quizzes. I don't know what's happening. You guys seem extra down. Are you down because you're all wanted to vote for Boot Edge Edge? Or Klobuchar? I'm sorry. Right? I don't know. I'm trying to figure out. Okay. There's some mass thing that's making everybody sad, and the thing that you all have in common is you just took a quiz. So I thought maybe that was what it was. You can make corrections. It's going to be relatively okay. All right. Maybe it's not that. Maybe you all hate me. And you're like, you have to be in this room with me. I'm sorry. Can't do much about that. All right. So I'm going to count that as our review of binomial stuff. Okay, I like it. So let's get into some new stuff. So what we're getting into now, chapter 4, one thing about binomial distributions. Are binomial distributions discrete or continuous? Think about it for a second. So what can you have? What's x in a binomial distribution? We just talked about it. What does x represent? The number of successes. So is that discrete or continuous? Discrete. 0, 1, 2. Does it skip anything? Yes, it skips an infinite number of things each time. Holy shit. You guys with me a little bit? Did it skip over 0.7? Can you have 0.7 people go to the festivities? You hope not. For so many reasons. Well, not many people and not even a whole person. You're like part art, I don't know, 30%. All right. So what we're about to do is we're going to get into a situation that's continuous. So things like time or age or anything continuous. So at first glance, this could seem like it's going to be really hard because a binomial distribution, if I went up to 100, that's got 0, 1, 2, 3, 100 parts. A continuous one has an infinite number of things because it's continuous. So I'm not going to make a table for it. We're actually going to make a visual of it. Okay, so one thing that is really nice, even if you don't play this game, you still know it. Anybody actually play darts? Not professionally. Has anyone ever seen a dartboard? Okay, all right. Let me start there. Anybody actually ever play just playing around? Anybody actually throw it in somebody's head? You too? Okay, all right. My brother has recuperated. We were young and we were unsupervised. Things happen. So here's my horrible rendition of a dartboard. It's like a close-up of some eyeball or something. All right, that's fine. There should be more triangles. Don't give me shit. So the main idea here is, why would you necessarily, in a certain way to play darts, why would you get more points for getting it here? Yeah, if you get it there consistently, why is that evidence you're a good player? Because if I was just throwing it over my shoulder, right, and only counting the ones that actually hit, so if it hits here, I don't count it. If it sticks in somebody's head, I don't count it. I race after them, say, give me that. If I was just throwing it over my shoulder, why would it be so unlikely to show up here? That when I stand over here, I realize it's not even in the middle, but oh well. Because what is it about? So why is it more likely to show up in one of these slices? Why would it be more likely to show up here than it would be to show up there? What is it physically about it? I heard it, the area. A larger, right? The area of that triangle-looking piece is larger. So the probability that me just randomly throwing darts up there is smaller for this because it's equivalent to the area in a sense. In fact, if the area of the dartboard was 1, and let's say the area of this is 0.06 or something, just to make something up. What's the probability that I randomly throw it here? 6%. It would be equal to the area of that place. So we intuitively know that this kind of thing is related to the area. That's why it's hard to get it in that. So if I'm looking at it and I get in that bullseye when I'm trying to consistently, that is evidence I'm good, because the chances I do that randomly is really low then. You guys with me? If I do it 5 times in a row, that would be 0.06 times 0.06 times 0.06 times. Holy shit. So is it likely I did it randomly? No, it's more likely that I actually know what the hell I'm doing, which I obviously don't. Not with darts. All right. So what's this got to do with us? We're not going to suddenly do dart math a lot. What we're going to do is this. Which way do I want to do this? We're going to work with what's called uniform distributions for chapter 5. Okay. So let me do this. Let me go ahead and give you this handout. I'm trying to figure out what order I want to do this in. This handout, we're actually going to use it a couple times this semester, so you want to keep track of this bad boy here. So it's got on there what looks like a Mayan pyramid in the middle, sort of. Try at the very top, try to fill that in real quick, those 2 problems. We'll do that real quick. I don't want to get too far away from this area idea, but still, you can do those real quick. So up here for flipping a coin, what would N be? 14. Of course, P and Q happen to be 0.5 each. I like it, 50-50 shot. We're assuming this is a regular coin. Nobody's tampered with it. So how would you set up the formula? Take a second. If you haven't done this yet, try to set up what the formula looks like for that first question. Getting exactly 9 heads. So give it the formula right here. So what would it be? They're probably getting 9 heads. How would you set that up? What would that be? 14. Choose 9. Good. I want 9 successes. So I'm well aware there's a little shortcut here. Let's see. But how many successes then? I would want 9. I just said that. So how many failures would I need? 5. Some of you guys might realize anytime P and Q are both 0.5, this is always going to be 0.5 to the n. If you don't know what I just said, but you get this, just do this. That's fine. So throw in the old calculator, see what you get. So you should get, so double check, make sure you can get this, 0.1222. It's about a 12% chance. Just did that too early. Yeah. Is everybody all right? You guys good? Yes?
How do you get the C?
Oh yeah, all right. So you just had to plug this sucker in. 14, go to math. Probability. Number 3, that's choose. 14, choose, what was it, 9, hit over. 0.5 to the 9th, hit over. 0.5 to the 5th. And that's how you get that. Is that all right? You guys all right? All right. What would you do for number 2? Yeah, figure out what, probably getting no heads. Figure out what that is and then do 1 minus that. So that formula for none would be 14 choose none. So I want no successes, I want all failures. You should get something very, very small, but thankfully we've talked about this already. What do you get?
0.000061 or 6.
Yeah, okay. Forgot what the times 10 of that was. So yeah, you get this weird ass thing. Please don't put 6. That means there's a 600% chance. That's gonna really freak me out. If I flip a coin and like 600 coins fall, 600% you suddenly create. No. What? No. Can't make any sense. So yeah, it should be really small chance that I get no heads, right? If I flipped a coin 14 times and got nothing but tails, I'm gonna go, huh? Who did something to you? Right? That would be evidence that it's been tampered with. Would it be proof? Would it be proof? What's the difference between proof and evidence? Proof means you know for damn sure. There's no other way. Evidence means it looks like it might be true, but I can't say. Right? You guys with me? We're not going to suddenly make this into a legal course or something, but. So what's the actual answer? It'd be 1 minus all this business. So it'd be 0.999939. Okay, maybe. Okay. So that's a nice little reminder. Now what I've done down here is I made a table. If I use the formula, can you see what 0 plus might mean? The probability of 0 is really close to 0, right? But of course it's a little bit above 0. So that's what 0 plus means in this thing. So I just copy this from this book I used to use. They only go to 3 places of the probabilities, but we'll give them a pass for that. Okay. And look, just to double check, the probability 9 is supposed to be 0.1222. So sure enough, 9.122, right? You guys with me? And then I took this and I plotted it. Now this I made. I will take full. This one I made. Aha. So I just graphed these in a histogram. Okay, remarkable, Jeff. So just to kind of remind you guys, this is made up of rectangles. So any probability formula, what's the area of this rectangle? Yeah, how wide is it? What's this? No, come on. 1, right? Can you guys tell me exactly what it goes from to? 4.5 up to? Kick ass. So it's 1 across, and how tall is it? 1.122. What's the area of that? 0.122. I like it. So again, it seems that, here's the point I'm trying to make with all this shit. If I graph a given probability distribution, if I can graph it, And you pretty much have to for continuous ones. If I can graph it, this is not continuous, but still, just to show you. If I can graph it, then the answer to any probability question will be equal to the area of that piece. Yes? Are you good? You're stretching. All right, I like it. Made everybody look at you, I'm sorry. Okay. Maybe. So, for example, if my distribution looked like a big box, and this is what it would look like, for example, if we lived in Germany. I actually went to Germany, and then I was in Italy right after that. And if you try to catch a train in Germany, you can set your watch to the train arriving. It's insane. It's like insane. Italy, the train was an hour and a half late, and I was looking at it, I was like, hey, what's going on? He's like, it's only an hour and a half. Holy shit. So it's a little different. So if you were somewhere, let's say you're in an airport and you have to go to a different terminal. Have you guys ever gotten on a shuttle or like a train or something? Let's say it comes every 15 minutes. If it comes every 15 minutes, what could happen? You could get there right when it's about to leave and just jump in before the thing is shut. So how long did you have to wait? 0. Or you can get there right after the door shut and it's going, so how long are you going to have to wait now? 15 minutes. Is there any reason that if you just randomly walk in there, that any amount of time should be more likely to wait? Doesn't it make sense? If you just randomly walk in there, it could be there, it could have just left, it could have left 7 minutes ago, it could be coming in 2 minutes. All of those are equally likely. Does that make sense? There's no reason any of them would be more likely, no matter how you feel about life. Right? We tend to remember the bad shit. That's why I always think it's more likely. Anyway. So, the one I'm talking about right now, let me see if I can borrow. Borrow you. Yes. So if I had a situation where we're 0 to 15, and they're all equally likely, so they all have the same, instead of being like this, where each one of them is a different probability, you with me? 7 is the most likely thing, which makes sense because 7 is the expected value. Yes, yes? But if I'm talking about this situation with the airport shuttle coming, they're all equally likely. This is called a uniform distribution. Because what do you think of when I say the word uniform? If I just said uniform?
The same.
The same, because you're thinking, what are you thinking? Somebody must be thinking in their head, somebody wearing an actual freaking uniform. Maybe it's got a hat. I don't know. Yes? Could be baseball uniform, could be cop uniform, could be whatever. Uniform means the same. I like it. Now watch. What did I just say earlier? If I can draw a distribution and the area is 1, whatever the shape of the distribution is, if I make the area 1,